This is Rosen 13.4, Discrete Mathematics and its Application. We are completing the proof of Theorem 2 that says a set is generated by a regular grammar if and only if it is a regular set, or based on an earlier theorem, if and only if it is recognized by an FSA. We've completed the only if portion of this proof, and now we complete the if portion. That is, if a set is recognized by an FSA, then it is generated by a regular grammar. So we begin by assuming we have an FSA that recognizes the language M prime, where our machine is M prime. Now we have a slight nuance that we need to take care of. We want to make sure we have a start state that is not revisited, so that if M prime has a start state that can be revisited, there's a lemma, which we don't prove, that we can create a new machine that is equivalent, we'll call it M, that has a start state that cannot be revisited. But if M prime already has a start state that is not revisited, we just let M equal M prime. In any case, we must start with a machine that has a start state that cannot be revisited, but we can always get there with an FSA. So what do? We need to construct a regular grammar, and we do so. Remember, it's the vocabulary, the terminal symbols, the start symbol, and the productions. And we'll build up each one as follows. The vocabulary is formed by assigning a symbol to each state and each input symbol of our machine. The terminal symbols are formed by the input symbols of the machine. The start state is formed from the start symbol S is formed from the start state of M, which is usually S0. And then the production rules are formed from the transitions of M. So that when a state S goes to state T on input A, we create, we have the non-terminal symbols A and T that are associated with those states. And I include the production AS produces the terminal symbol A followed by AT in my production rules. And I include AS produces the terminal symbol A when T is a final state. And then I include S produces lambda if the start state of M is final. And that will produce that grammar will produce the language that is recognized by our machine by construction. All right, let's take a look at an example. Here I have a finite state automaton that I want to create the grammar that recognizes the same language. In order to have a start state that is not revisited, I need to assign symbols to each of my states. And then the inputs will also be part of my vocabulary. And then I'll need to create the production rules to complete my grammar. I'll start with S. So S produces 1A since it goes to state S1 upon input of 1. But since state A is final, S also produces 1. S produces 0C, but since C is not final, S does not produce 0. I don't have S producing lambda since state S0 is not final. Well, that takes care of all the transitions out of state S0. Let's look at state S1. We associate that with A. So A produces 1A, but A also produces 1 since state associated with A is final. And then A produces 0C, but not 0 since C is not final, or S3 is not final. That takes care of all the transitions from state S1. How about the state S3? C produces 0C. but not 0. And C produces 1B because it goes to S2 on input of 1. And since S2 is final, C also produces 1. And now that covers all the transitions out of state S3. Now let's go to state S2. We associate that with B. It produces 1B, but it also produces 1 since B is final. And B produces 0B, but it also produces 0 because B is final. And that takes care of all the transitions out of S2 and all the transitions for our finite state machine. And this grammar will produce the language that is recognized by this machine.